So this is the 10th lecture. In this lecture, we're going to introduce the topic of continuous random variables. And so I have to warn you that traditionally when students take introductory probability courses, this exact point in the learning process where continuous random variables are first introduced represents the biggest jump in difficulty. So, continuous random variables require calculus to analyze, and they're much harder to think of concretely in terms of sample spaces and measurement functions, which work so well for discrete random variables. So, if you feel like you're not grasping the material in this lecture and the next few lectures as well as you grasped the material in the previous lectures, that's not at all unusual, and while I'll attempt to minimize it, it's pretty much inevitable in a probability course just because this concept of a continuous random variable really does involve much greater mathematical abstraction than everything we've been talking about so far. However, I'll try to do my best to explain things clearly. So, a continuous random variable represents the idea of a random real number or a random point in a geometric space. So, continuous random variables are often referred to just as distributions, and when you can think of it as like a random point being distributed in a space. So, like, the simplest example is to think of the unit interval. So, all the numbers between 0 and 1 as some sort of little stick of length 1. And then you're just choosing a random point on that stick and measuring the point you chose. And so if you label one end of the stick 0 and label the other end of the stick 1, you can construct a random variable by choosing a random point in this. You can construct a random variable by choosing a random point in this little stick of length 1 and measuring how far it is from the 0 end. So, what we're going to do is parallel the three forms of defining a discrete random variable. So, if you remember, the discrete random variables could be described with measurement functions, which are the most concrete way but the hardest to work with. And measurement functions involve explicitly specifying a real number for every element of the sample space. And in the theory of continuous random variables, we also have measurement functions which play exactly the same role as they do for discrete random variables, but measurement functions very rarely come to the surface in the theory of continuous random variables, and often they're just suppressed entirely. So it's highly inadvisable to think about continuous random variables in terms of measurement functions until you're extremely familiar with the more effective methods of thinking about the other two definitions for continuous random variables. Okay, so the second way we had to define a discrete random variable was we had this thing called a probability mass function. And so the probability mass function was a function that took as input a potential value of the random variable, and it took as output, or it produced as output the probability that the random variable was equal to that value. And so the most important idea in understanding continuous random variables is there's an analogous but substantially different concept called a probability density or a probability density function. So you should think of probability densities as the main way of defining continuous random variables, and I would even go so far as to say as you should just pin your idea of continuous random variable down to this concept of probability density. So you can think that anytime I'm thinking about a continuous random variable, what I want to do is think about a probability density. And so what's a probability density? A probability density is a function from the real numbers to the real numbers, which allows you to compute the probability that the random variable falls in a specific interval by integrating the density over that interval. So a probability density is always a non-negative function with total integral equal to 1. So the notation I'm using for probability density here is q with a subscript x. So x is the random variable, and we're indicating that the probability density q is associated with the random variable x. And so what that means is we have this function qx from the real numbers to the real numbers. And the way this function qx defines everything we need to know about the random variable is we can figure out the probability that the random variable lies within a specific interval of numbers by integrating the probability density over that interval. So if you kind of think about the way this works, we have some function q of x, which is always greater than or equal to 0, and the integral from minus infinity to infinity is 1. And so if you think, okay, what happens if I plug in a equals something really negative, close to minus infinity, and b is some huge positive number close to infinity? Then the integral of q is going to be really close to 1, because the integral over the whole line is 1. And what that tells you is if you take some gigantic interval and you put a really negative lower bound and a really positive upper bound, then the probability that the random variable falls in that gigantic interval is very high. It's close to 1. On the other hand, if you, let's say, you pick a is minus 0.0001 and b is 0.0001. So you pick a tiny little interval where A is just a little bit less than B. Then what ends up happening is you have this very, very short interval where you're integrating the density. And because the interval where you're integrating the density is so short, it ends up giving you a very small number for the probability that this random variable is in this tiny little interval. And if you go to the most extreme case where A is actually equal to B, you get the integral over a trivial interval where you just have integral from B to B of Q, and that comes out to be 0. So a continuous random variable has 0 probability of being equal to a precisely specified real number. This is what I was talking about, if you recall, in the lecture where I introduced the concept of infinite sequences of events. I gave you this example where I said I was trying to horrify you with the terrible contradictions that would happen if you indexed things by real numbers and started working with events indexed by real numbers as if they were indexed by discrete numbers. And so one important consequence of that rule that you're not allowed to index events with real numbers is you're not allowed to claim that just because X has a 0 probability chance of being equal to any specific real number, therefore it has a 0 probability of anything. Because going from 0 probability for a specific real number to 0 probability for the whole interval requires you to jump over indexing things with real numbers. There's too many specific real numbers to make that conceptual leap. In order to make that conceptual leap, you would have to have discrete numbers instead of real numbers. So even though it's 0 probability for X to hit any value with precise no error, there's still positive probability of X lying within non-trivial intervals where A is strictly less than B, and that probability is calculated by integrating the density Q. Okay. And there's also a concept of cumulative distribution function for continuous random variables, but because it's exactly the same as the concept for discrete random variables, I won't say anything more about it than just to say it's the probability that the random variable is less than or equal to a specific value. So the message I want you to take from this introductory definition of continuous random variables is what's highlighted in teal, that the most important way to think about a continuous random variable is this probability density function, Q sub x, which tells you the probability of X being within an interval by integrating over that interval. Okay, so let's see an example of continuous random variable. So this is what's called the standard uniform distribution. So in this case, the sample space is the unit interval. So the sample space is all the numbers between 0 and 1. And the probability on this sample space is just length. So it's like throwing a dart at a line on a wall where you have no control over where it hits, and you're like, okay, I'm just going to say, well, the probability that the dart lands in some set is the length of that set, because I'm assuming that it's uniformly distributed over this interval of length 1. And then the random variable we want to consider is x of t equal to t. Okay, so you can see on the top right, I have the probability density for this random variable. So the density is equal to 0 if the input is less than 0, and it's equal to 0 if the input is greater than 1. And it's equal to 1 if the input is in the unit interval. So you can see I have in red the graph of this function. It looks like a step of length 1 over the unit interval. And on the bottom left, I have a verification that this really is the density for the standard uniform distribution, because I've seen that the probability that the random variable is between A and B is the probability that t is between A and B. And so I'm looking at all the length of the set of numbers which lie both in the interval 0, 1 and the interval AB. So I'm intersecting two intervals. I'm intersecting the unit interval with the interval from A to B. And so when I intersect the unit interval with the interval from A to B, the length of what I get is the minimum of B and 1 minus the maximum of A and 0. And you can verify that's exactly what you get by integrating this density from A to B. And so because densities are so important in the theory of continuous random variables, usually we don't even bother specifying the sample space or the underlying probability at all. Instead, what we do is we write it like the notation I have at the very bottom left of the page, where we write something like x, which denotes the random variable, and then we write this little tilde and write, in this case, uniform 0, 1 for the density that we're trying to consider. So basically what this notation is supposed to do is it's supposed to say that we're not even going to consider sample spaces or measurement functions at all. We're just going to focus completely on densities. Okay, so at the bottom right of the page, you can see I've drawn the cumulative distribution function. And so the cumulative distribution function is always going to be continuous. And so if you remember, there was a problem on homework 3 where you had to find an answer of pi for appropriate frequency in the sine function to cancel out discontinuities in a step function style cumulative distribution for a discrete random variable. But I guess the reason that continuous random variables are called continuous is because their cumulative distribution functions are continuous functions on the real numbers in the sense of elementary calculus. And so, you can see this cumulative distribution function. If we're picking this random real number, we're picking a random real number between 0 and 1. So we're picking a random real number between 0 and 1, and the chance it's less than 0 is nothing, And then as you progress from 0 to 1, the chance that your random number is less than that increases until you get to 1, and then the chance your random number is less than 1 is perfect because you said your random number was between 0 and 1. Okay. So that's the standard uniform distribution, which is the simplest of all continuous random variables. So now we're going to think of a generalization of the standard uniform distribution. The generalization is that instead of focusing on the unit interval and thinking of length as our probability, we're going to think of a general interval in the real numbers from alpha to beta. And we're going to say that the interval is non-trivial, so alpha is less than beta, and the probability we're going to deal with is the length divided by the length of the total intervals. So instead of throwing a dart at a line segment of length 1, we're throwing a dart at a line segment of length beta minus alpha. And in order to get a correct probability that satisfies the axiom of certainty, we can't just take length, because if we take length as our probability, we're going to violate the axiom of certainty unless beta minus alpha is equal to 1, because the length of the whole sample space would be beta minus alpha. So instead, in order to make sure we conform with the axiom of certainty, instead of just saying that probability is the same thing as length, we're going to say that probability is length normalized by the total length of the intervals. So if alpha was -1 and beta was 1, probability would be length divided by 2. And it makes sense if you think I'm choosing a random real number between -1 and 1, the chance that it's positive is a half, because you have this total interval from -1 to 1, and the probability that you're in the right half of the interval is the length of the right half, which is 1, divided by the total length, which is 2. Okay, and the random variable we're considering is, again, just given by x of t equals t. Okay, so you can see the density I have written on the upper right. In the density of the general uniform distribution, you also have a step function, but now the height of the step is no longer 1, as with the standard uniform distribution. Now the height of the step is 1 over beta minus alpha. And you can see that's what needs to be the case based on the computation on the lower left. So we want to take the probability that of the set of all outcomes between alpha and beta, which are also between A and B. So we're picking this random number between A and B, or we're picking this random number between alpha and beta, and we're asking, if I'm picking a random number between alpha and beta, what's the probability that it lies between A and B? And so you can see that what we end up doing is, again, intersecting two intervals. So if you go back to the standard uniform distribution, in the second line of the computation on the lower left, where it says probability that t is of t in 0, 1, such that a is less than equal t less than equal b. What we're doing there is we're intersecting the interval from 0 to 1 with the interval from a to b and computing its length. So what we're doing in the same step of the computation here is we're intersecting the interval from alpha to beta with the interval from a to t. And instead of taking its length, which is minimum of b beta minus maximum of a alpha, instead of taking the length of the intersected interval, we take the length and normalize it by dividing with beta minus alpha. And you can see that's what we need to do, because if we set b equal to something way bigger than beta and a equal to something way less than alpha, we're asking, I'm picking a random number between alpha and beta, and I'm asking what's the probability it's in this gigantic interval which completely contains alpha to beta. And so the probability of that needs to be 1. So if I plug in something bigger than beta for b and something less than alpha for a, the minimum picks beta instead of b, the maximum picks alpha instead of a, and I get 1 over beta minus alpha times beta minus alpha, which gives me 1. And so you can calculate that this formula where we're intersecting the interval from alpha to beta with the interval from a to b and taking the normalized length is exactly what I get by integrating this density q, where I have a step function supported from alpha to beta with height 1 over beta minus alpha. And again, because densities are the primary way of thinking about continuous random variables, when we're dealing with the general uniform distribution, we're going to, rather than introducing sample spaces and underlying probabilities, we're just going to write x is distributed like uniform alpha beta. So this little tilde symbol we want to read as is distributed as, so we're saying at the very last line on the left, x is distributed as uniform alpha beta. Okay, and then the cumulative distribution function of general uniform distribution is this thing which looks very similar to what it did when we had the standard uniform distribution, except now the slope of the line is different. Now, instead of being a line of slope 1 from 0 to 1, the inclined part is a line of slope beta minus alpha from alpha to beta. Okay, so the next example we want to consider is what's called the standard normal distribution. And so when I just throw this distribution at you now, if you haven't seen it before, it's not at all obvious why anyone would think about this. Like, there's a very clear physical analogy to picking a random number between 0 and 1, and the standard uniform distribution just mathematically formalizes the concept of a random number between 0 and 1. But this thing I'm talking about here, the standard normal distribution, it's not at all clear what the physical analogy it's supposed to convey is. The physical analogy it conveys is a very deep theorem, which is known as the central limit theorem, and will be the culminating topic of the course. That is the last thing we'll do before, or the central limit theorem, where the standard normal distribution becomes super important, is the last thing that will be on the final exam, and it's the most powerful tool for real world applications that we're going to learn in this course. So, this standard normal distribution I'm introducing to you now, I'm just going to have to kind of introduce on a promise that if you're not already familiar with it, it's going to become super useful at the final stage of the course where everything kind of comes together and we get the most powerful tools for real world probability. But until then, you'll just kind of have to take it on faith that this thing is something important, because I can't give you an easy physical analogy for it like I can with the standard uniform distribution, where you're picking a random number between 0 and 1. Okay, so because there isn't an easy physical analogy for the standard normal distribution, I'm going to completely avoid the issue of specifying a measurement function for it or an underlying sample space. So I get that that's epistemologically dishonest of me, because sample spaces are the underlying structure of the axioms of probability, and measurement functions are how random variables connect to the axioms. But in order to really go through in detail how to think of an explicit measurement function for the standard normal, I would have to introduce a lot of theory that is not relevant to the more problem-solving oriented aspect of this course. So I'm just going to tell you, as I did before, that densities are the most important way of thinking about continuous random variables, and the standard normal will only define in terms of a density. So you can see the density I have, Q of x, is written on the upper right here. The density is 1 over the square root of 2 pi e to the minus s squared over 2. And so 1 over the square root of 2 pi is a normalization factor which ensures the integral of the density over the whole of the real line is 1. So this density is also known as the bell curve or the Gaussian. So the bell curve is kind of the mascot of probability and statistics, because it represents this standard normal distribution, which is the heart of applying probability and statistics via this thing I'm hyping up called the central limit theorem that will come at the end of the course. So because the central limit theorem is primarily about the standard normal, and the central limit theorem is what everyone thinks about in applying probability in the real world, this bell curve that is the graph of the standard normal is kind of the visual image that most people associate with mathematical probability. And if you're familiar with kind of the non-technical social interpretation of the bell curve as kind of something that you often see in reality for charts of how things like height or prevalence of disease or annual temperature or just, you've seen this image so many times in your life with graphs of real world physical quantities. And the mathematical reason it shows up as the graph of so many physical quantities is because the graph of this mathematical function q I have at the top right is what the central limit theorem is about, and the central limit theorem is the engine that makes mathematical probability run when applied to science. Okay, so we're going to use the symbol x is distributed as n01 for a random variable with the standard normal distribution. And you can see I have the cumulative distribution function of the standard normal in green at the bottom right. So unlike the cumulative distribution function of a discrete random variable, the cumulative distribution of a continuous random variable doesn't necessarily have to max out 1 at some finite point and spend a right infinite interval exactly at 1. It can spend perpetuity slightly less than 1, limiting asymptotically up to 1 as you go to infinity. And that's what happens with the green curve that shows the cumulative distribution of the standard normal. The reason the cumulative distribution never actually maxes out to 1 is because the red bell curve, which is the density, never actually decays all the way to 0. So if you have a bell curve, there's always a probability of having an outlier no matter how extreme. It's just that probability decays insanely microscopically once you get out really far away from the central hump of the bell curve. But the bell curve never actually decays to 0, and you always have some, almost invisible probability of getting an extreme outlier, which is nevertheless positive. Okay, so we can see another example of generalizing from a standard construction to a more general construction. And this is what we're going to call the general normal distribution. And so I promised you that the standard normal distribution would be important because it comes out of this thing called the central limit theorem, and the general normal distribution also plays a very important role in central limit theorem based applications of probability in science. So the general normal distribution gives you more freedom in how you're structuring your bell curve. So the standard normal is centered at 0, and it has a variance of 1. I haven't explicitly defined expectation and variance for continuous random variables. I'll do that on the next page, but the reason for passing from the standard normal to the general normal is the general normal allows you flexibility with the mean and variance. So in scientific applications of probability, it's often important to adjust the parameters of your distribution based on information you have about the specific empirical phenomenon you're observing. And what the general normal distribution does is it takes the standard normal, which is so tremendously prevalent because of this deep fact called the central limit theorem, and it allows you to apply the same strategy for understanding the world to a wider variety of contexts where you're not always insisting that the average is 0 and the variance is 1. So what the general normal distribution allows you to do, allows you to choose a parameter mu for the expectation of the general normal, and mu can be any real number you want. You can center the general normal at any point. And then you have to choose another parameter which needs to be positive, because the second parameter you choose, sigma, is the standard deviation, which is the square root of the variance. And variance is always positive, so standard deviation is always positive. So in order to parameterize the general normal, you choose a parameter mu for the expectation and a parameter sigma for the square root of the variance. And then you have this weird looking function. 1 over q of x is 1 over the square root of 2 pi times sigma e to the power of minus x minus mu all squared over 2 sigma squared. And I can't really tell you anything better about how to interpret that formula other than to just go through the process yourself of figuring out why the graph of that function is this bell curve I have drawn right below it, where the central point of the peak of the bell curve is mu, and the height of the bell curve is 1 over square root 2 pi sigma. And so this is the general normal distribution, and you can have a very concentrated normal by choosing sigma to be really large. So, or sorry, you can have a very concentrated normal by choosing sigma to be very small. So if sigma is very small, you're going to have an extremely high bell curve with a very narrow range of support. And in that case, you have very low variance. And if you choose a really large value of sigma, you'll have a shallow, flat bell curve with a wide base of support, and in that case, you'll have a very high variance. Okay, so expectation and variance of continuous random variables involves integration over the entire real number line rather than summation over the potential values of the function as with a discrete random variable. In higher math, where you approach probability from a standpoint of axiomatic real analysis, it is possible to come up with a general concept that unifies both continuous and discrete random variables. And with that higher level concept, you can implement both the continuous expectation formula and the discrete expectation formula as two versions of the same concept. But at an introductory level in probability, it's unfortunately obscure what exactly the relationship is between the continuous expectation formula and the discrete expectation formula. Like, if looking at the two formulas gives you some intuition about why they're related, with integrals connected to sums and S connected to the value V and Q connected to the probability mass function, then that's great. But I'm not going to really try and sell you on the idea that at this level in an introductory probability course, it's clear why this continuous expectation formula is the right analog of the discrete expectation formula. But, hopefully you can understand what the continuous expectation formula means. You need to take the integral from minus infinity to infinity of x times the density with respect to this variable s. So the continuous variance formula you can see highlighted in the teal on the bottom. So it has a similarity again with the discrete variance formula in that you have these two different versions. One which is used as the initial definition, where I have integral of s minus mu all squared qxs ds, and that formulation makes it transparent that variance is always positive because the square is positive and the density is positive. But the formula highlighted in teal at the very bottom of the page is the one you want to memorize as the continuous random variable variance formula. You integrate from minus infinity to infinity s squared times the qx of s ds, where qx is the density, and then you subtract the square of the expectation. So you're never, ever, ever going to be able to calculate the variance without first calculating the expectation. And then once you've calculated the expectation, it's just simpler to do the integral with s squared and subtract mu squared after. Okay, so we can see an example. There's nothing really conceptual to this example. It's just plugging in definitions that already appeared in the pages of this lecture, but we can say we have alpha and beta with alpha less than beta, and we're going to let x be distributed as uniform alpha beta. And we want to calculate the expectation of x and the variance of x. So we can copy from example 10.2 the density of uniform alpha beta is 0 if the input is less than alpha or greater than beta, and 1 over beta minus alpha if the input is between alpha and beta. So we can apply the continuous expectation formula. We need to integrate from minus infinity to infinity s q of x s ds. So what happens? Well, this density is 0 outside the interval from alpha to beta, so we can just completely drop everything from the integral except alpha to beta. And then on the interval from alpha to beta, it's just giving us a constant 1 over beta minus alpha. So really, we just have the integral of s ds, and we can integrate s ds from alpha to beta, and get beta squared minus alpha squared over 2, divide that by beta minus alpha, and use difference of squares on the top to get beta plus alpha over 2. So here we've recovered the concept of an average that people drawing in the sand knew before they even thought about numbers, where an average is the sum divided by 2. So the, if you have two clay urns. You can average them by pouring wine from one to the other and making them roughly equal. You know, people, that's how you can average without numbers. But anyways, here we've recovered the concept of expectation as the simplest idea of an average, sum divided by 2, with expectation of uniform alpha beta is beta plus alpha over 2. And then for the variance, we need to calculate integral from minus infinity to infinity s squared q of x s ds. And so, again, the density vanishes outside the interval from alpha to beta, so that just squishes those parts of the integral, and we only need to integrate from alpha to beta. We have s squared divided by the normalizing constant, and then we're subtracting what we previously calculated for the square of the mean. So we're integrating s squared from alpha to beta. We get beta cubed minus alpha cubed over 3. Divide by beta minus alpha and subtract the square of the mean, and this all simplifies out to beta minus alpha squared over 12. So that's the variance of the uniform random variable. In particular, if you set beta equal to alpha, or sorry, no, if you set beta equal to 1 and you set alpha equal to 0 in order to calculate the expectation and variance of the standard uniform random variable, what you can see is that the expectation of the standard uniform is a half. So hopefully that agrees with your intuition that I told you physicists think of expectation as center of mass, and if you have a stick of length 1, the center of mass is a half. And then the variance of the standard uniform is 1/12. Okay, so in the lecture there, we'll have the we'll have the interactive lectures on Monday without necessarily having working on a specific homework, because homework 4 will be assigned on Monday and will be due on March 22nd.